Okay, I'm going to try this out. I'm going to try to use Word just because I can't really find anything that works any better than Word right now as far as writing this stuff out goes. So bear with me as I kind of learn as I go. So this is going to be the first video here. So picking up where we left off in class last time, we're going to jump into 10.5. I'll probably split this up into two different videos because it's a pretty long section in general. But we're just going to jump right into it. So 10.5, we're going to be looking at a couple of new topics that we haven't seen so far, in particular this idea of absolute convergence. So before we get there, let's just look at a couple different examples. So if we look at this series as n equals 0 to infinity, we're looking at 5 times negative 1/4 to the n power. And just to write out a couple of these terms so you can visualize what this is going to look like. First term is going to be 5 when we plug in n equals to 0. My next term is going to be negative when I plug in n equals 1, so negative 5/4. And then just to fill out the rest, 5/16, and then negative 5/64, and then this will just keep going on forever and ever and ever. Okay, so this is a series that we've seen before. This is just a geometric series. So from the geometric series, you have our a value, and then we have our r value based on the n. This does converge. Since our r value here is less than 1, since our r is equal to that negative 1/4, which is fine. Remember, it can be negative. It's really the absolute value of r has to be less than 1 for this to converge. Okay, so we're also going to look at another series here. If I can hit the right button. So very, very similar series, but now we're looking at the series as n goes from 0, or sorry, not 0, it should be 1 to infinity, of 5 times just positive 1/4 to the n. And so what this series is the same series. It's just that instead of having those negative terms that alternate, we're going to be having just positive terms the whole way down. All right, but this series compared to this series, it's still a geometric series, and it's still going to converge as the n goes to infinity. Because our r value is less than 1, this is a geometric series. This brings up an important definition. This is something called absolute convergence. So a quick little definition here. A series converges absolutely if the corresponding series absolute value of our a sub n. Oh, crap. Sorry. I did it again. There we go. Converges. I'll read back over this. So, a series converges absolutely. This is our definition here. Converges absolutely if the corresponding series of the absolute value terms converges. So notice that this series, this top geometric series with the negative alternating terms, this doesn't just converge. It actually converges absolutely, because if we look at the same series but all positive terms, this converges. So because the absolute value series converges, then we can say that this series converges absolutely. Just a little bit more powerful of a statement. Okay, and then from this, we get a little theorem. So that theorem says this. If we have a series as n goes from 1 to infinity of the absolute value of a bunch of terms, so if this converges, then we automatically get that the other series, the one that does not have the absolute value, converges. Okay, so very, very powerful and very, very important theorem here. If the absolute value terms is something that only has positive terms converges, then if I make some of the terms or half of the terms or all of the terms negative, we get another series that converges. All right. So I have a little proof to this, but I'm going to just skip over it just because I don't feel like writing it all out. But let's look at a quick little example. So if we have the series as n goes from 1 to infinity of negative 1 to the n plus 1 of 1 over n squared. Okay. So this negative 1 out in front as my n keeps increasing, this is just going to alternate my terms. We can actually write out some of these terms here. So my first term, if I plug 0 in, negative 1 to the 0 power is just 1, and this is going to be, so not putting 0, I'm putting 1 in. If I plug 1 into this, 1 plus 1 is 2, so that's squaring that to make that a positive 1, and this is going to be 1 over 1, so 1. If I plug 2 into it, I get a negative 1/4. If I plug 3 into it, positive 1/9, then negative 1/16, and then, forever and ever and ever. So my terms alternate positive, negative, negative. But I don't even have to do anything here because I know that this converges since we've already looked at a series before, the series of 1 over n squared. Remember that this has a name to it. This is what we call a p-series, and because this exponent is bigger than 1, this converges. All right, so we can say that the example here, this converges because the absolute value series converges. So that's that absolute convergence. So that statement up here, this we could say converges absolutely. Okay. So the whole point of telling you all this is to bring up something very, very important. I'm going to start this, the ratio test. Not a ration test, it's ratio test. The ratio test is probably the test that you are going to use more often than not. This is probably the most powerful test that we're going to have. So let me just write out the definition here. So let there be some series of these sequence terms, a sub n. So let that be any series. And also suppose that we look at the special limit. So this limit that we're going to look at here, the limit as n goes to infinity. Oops. So as n goes to infinity. There we go. And then the thing that we're trying to take the absolute value of is going to, or sorry, we're trying to take the limit of is the special absolute value. It's going to be a ratio, of course, because it's called a ratio test. So this ratio that we're trying to do is going to be the sequence term a sub n plus 1 divided by a sub n. All right. This is going to be the ratio test in general. We're going to write out some more to this here in just a second. But if we have this series where we're just adding a bunch of sequence terms, then if I take the limit of the ratio of those sequence terms as the absolute value as n goes to infinity, if this comes out to be some number, I'm just going to call it p. Then there's a couple of different things that could possibly happen. If that p comes out to be less than 1, then the series converges absolutely. So if the ratio of the sequence terms comes out to be a number that is less than 1, the series converges absolutely. The series diverges if my p comes out to be greater than 1, or if p comes out to be converges to infinity. And then C, the test is actually inconclusive if the p comes out to be exactly 1. All right, so just to go over the ratio test again, if you take the limit of the ratio of the next term divided by the previous term, the absolute value as n goes to infinity. This may converge, it may not converge. If this does converge to a number, and that number is less than 1, the series converges absolutely. If it converges to a number and that number is bigger than 1, it diverges. If it comes out to be equal than 1, then the test is inconclusive. All right. So I'm probably going to stop this video here. I'm going to pick up in the next video, and we're going to look at a bunch of different examples.